Hi guys, in this video we're going to be looking at completing the square. Really is kind of a neat method for solving quadratic equations especially. And so I know that it's not everybody's favorite thing to do, but it is really effective at helping us solve equations that are quadratic in this form here. So let's take a look at this equation here. What I'd like to do is to find the zeros of this function, and then we're going to verify them by sketching a graph and identify some max or min values and where they occur. So taking a look at this function to begin with, I'm going to replace f of x with y. But we're going to go ahead and rewrite the function down here, y equals x squared plus 4x plus 2. And we're just going to go through our steps for completing the square. So let's start with moving our constant to the left side here. I'm going to subtract 2 from both sides, which gives us this form right here, x squared plus 4x. Now, I notice that our leading coefficient here is 1, which is really great when that happens because it means that we don't have to factor out any a value that might exist up here other than 1, which would not change the values on either of these terms here. So I'm going to go ahead and build in, say I guess a blank space here. You know what, just to give us some space, why don't I do this on both sides here? I'm going to build in this constant here that I'd like to have exist that would cause this right-hand side to be what we call a perfect square trinomial. So now remember, your constant here, we want it to be equal to half your middle term squared. And so if our middle term is 4, half of 4 is 2, and 2 squared is 4. We're going to put a 4 here, and what we add to one side, we have to add to the other. So on the left side here, combining like terms, looks like we get a y plus 2. On the right side here, now remember, this was the whole intent of adding this half of the middle term squared back here. We wanted this to be able to factor, and the fact is, remember that anything in this form here, x squared plus bx plus half of b squared, if it looks like this, okay, then it has to factor into x plus b over 2 squared, or a square of a binomial. And that's, remember, where this gets its name, a perfect square trinomial. It's a perfect square trinomial because it's a perfect square of this binomial here. So when I write this binomial, remember that I just want to put half my middle term in this quantity here. So 4 over 2, or in this case, I suppose I could put a 2 here. And so looking at what we have right here, I'm going to go ahead and do something. I'm going to move that 2 back to the right-hand side because I do want to look at this as something that is in what I've been calling standard form and what I'm going to start to call vertex form. Just because this form here ultimately tells us where the vertex is initially at h and k, which are these two values here. But I'm going to put it in this form before we kind of look at what it is that we want to do first, because when I say find the zeros of this function, remember, what are the zeros of this function? These are these x values that when I plug them in here, I'm guaranteed to get a y value of 0. And so why is completing the square kind of an effective method for solving for zeros? I'm going to go ahead and kind of set this aside here. I'm going to write zeros and have you do the same thing here. We're going to bring this equation over here, but we're going to substitute 0 in for y, and we're going to go solve for x. And the neat thing about having it in this form is whenever you have something in this form, it's kind of looking at it as I have a quantity that's being squared, and my x is on the inside of it. So if I could get the squared quantity by itself, we could just use square roots on both sides to undo the squared. So that's exactly what I want to do here. I'm going to add 2 to both sides of this, and so what we get is 2 on the left. On the right-hand side, we have x plus 2 squared. And so now that we've isolated this squared quantity, we're going to go ahead and take the square root of both sides. And the thing here is we get just x plus 2 on the right, but on the left we have to write plus or minus the square root of 2. We took the square root of 2, we got to write plus or minus. And so to solve for x, you notice now all I have to do is subtract 2 from both sides. I'm going to give you some advice because this is going to happen a lot with this plus or minus. Let's put the non-plus or minus number first. So like negative 2 plus or minus the square root of 2 equals x. And what I'm going to do is, first of all, I'm going to scroll down a little bit here. There we go, and see that a little bit better. I'm going to put a box around this. And I want you to realize that this is two solutions, two zeros. The first one is x equals negative 2 plus the square root of 2, and the second one is equal to negative 2 minus the square root of 2. And so we're going to get a decimal approximation for these in just a moment, but what I did want to do was also sketch this. And so back to another benefit of having something in this, what I'm going to call vertex form now, this ax minus h squared plus k form, is that it's really easy to graph these just by identifying transformations that are going on. So if I look back at this equation over here, I know that this is a quadratic function that isn't stretched or reflected, at all, but would go left 2 and down 2. So if I were to sketch this here, I go left 2 and down 2, assuming I'm going by a scale of 1 here. Here's my vertex value, and so I'm going to label this, because I know it opens upward, I'm going to just go ahead and label it kind of down here below it. And I know that my a value here is 1, so quadratic things that have the same width as their parent function tend to go from this point up 1, right 1, and up 2, right 4. And so if I go up 2, right 4, that kind of puts us at 2 above the x-axis here on this side. And because of symmetry, our axis of symmetry here would have to be x equals -2, since it has to have the same x value as our vertex value here. I know that these points exist on the left-hand side as well. And so I'm going to go ahead and place those on our curve and say here it is. So now, a moment ago, what we wanted to do was find the zeros of this function. So what I want to make sure I point out here is that the zeros of this function are these two x values right here. And what we can witness is that one of them has to be between -1 and 0. And this is -2 right here, so -3 and -4, one of them is between -3 and -4. And so we kind of want to be able to narrow it down here. So getting your calculator out here, we can go ahead and type these in independently of one another. I'm going to write -2 plus the square root of 2 and show you a neat function on this calculator here, but plus the square root of 2, we get enter here, -0.59-ish. And I'm going to hit second enter, and I want you to notice that what happens is the last expression pops up that you just typed in. So that way you don't have to type the whole thing in again. We can just go replace this with minus, and we get this. And so remember, we said we were looking for two zeros, one between -1 and 0, and the other one between -3 and -4. And so these are our two zeros right here, -0.59-ish and -3.41. And so this would be our -3.41 and -0.59, and these are both ish, okay? And so these are our two zeros here. So pretty neat. We're able to find these exact values, which is the most important thing, and then we can get decimal approximations that we can, verify using our graph as well. So last thing I wanted to do was identify max or min values and where they occur. We would want to say that this graph goes from decreasing to increasing when x equals -2. And so if that's the case, then we have a minimum value here. I want to highlight something here. The minimum value is the y part, and then the location value is the x part. And so I suppose we could say we have a min of, oh, that's a horrible n, min of -2 when x equals -2. And so that's the important thing. We just distinguish between the value of the minimum and the location of the minimum here. Cheers.